Okay, here we are again, and I have the same answer. What I realized I did is I plugged into the calculator wrong. So, goodness, I had all the right work, but then I plugged into the calculator wrong. Let's go ahead and re-look at the calculator. Okay, so it was literally as simple as me putting a minus right there in front of the E. But, hey, now we know we're right. Let's check with the negative answer also. The minus square root of 63. It's not a negative answer, but let's check with the ln of 8 minus the square root of 63. See what we get there. Okay, so once again we're seeing that we're getting 16. So we have two answers. We want to keep both of them for our solution. All right. Let's go ahead and move to the next problem, but before that we're going to hear a word from our sponsor. Thanks to YouTube for making this whole study session available to us. We really appreciate you, and appreciate you also giving us the ability to listen to the Czechoslovakian national anthem. Really like the things that you offer, YouTube. Thanks a lot. Let's get back to math. Alright, so number 21, we're going to use the data in the table and assume growth is exponential to find when the populations of Columbus and Austin, to find out when they're going to be equal to each other. We want to round the base to the 5th decimal place. We want to find a couple exponential equations that represent the populations. So let's go ahead and get started with Austin. Okay, so I have the population, I have P sub 1 representing Austin here because we're going to use P sub 1 because we're going to look at second city also. We're going to do that P sub 2. So the population with respect to the time is given by this exponential equation. Here we have our initial population when the time is equal to 0, that's 1900. And what we want to do is we want to figure out the B value here. So let's go ahead and plug in the population after let's see, 100 years actually. Okay, so what I've done here is I've used the exponential model to plug in the initial population of Austin, and then I plugged in time at 100 years beyond the initial population at year 2000. We've gone 100 years beyond. Here our population is equal to 656,562. And so we need to solve for the base here. So I'm going to divide both sides by 465,622 and then take the raise both sides to the 1/10 power. Alright, so gosh, my mind's all over the place right now. So I don't feel like I'm doing a good job explaining. So sorry. Just dealing with family at the same time. So anyway, sorry. So I have B equals our population times our populations divided to the 1/100th power. Okay, so let's go ahead and see what the B value is on our calculator. Remember, we're going to round the base value to the 5th decimal place. Okay, so here we have our B value. Let's go ahead and rewrite this exponential equation so that we can identify populations. Alright, so here we have the population of Austin exponential equation, and that will enable us to identify what the population is after a certain amount of years. We want to do the same exact thing for the Columbus population. So how about this? I'm just going to go ahead and show you the work and then talk about it, okay? Okay, so I have found the exponential equation that models Columbus, Ohio's population. And so what we want to do is we want to figure out when the populations of Austin and Columbus are going to be equal to each other. So essentially what we want to do is set both of these equations equal to each other and solve for the time. Well, we're going to use a calculator to do that. Let's go ahead and plug in these population models into our y sub 1 and 2 spots on the calculator and look at the graph to see where they both intersect each other, because that's where they're going to be equal to each other. Alright, so here I have the two equations entered into the calculator, and I want to see where they're both equal to each other. I want to see where the two equations intersect. Now, this is the part where a lot of you were struggling, because you would do something like a Zoom 6 and you'd say, I can't see anything, what's going on here? Well, your window's not right. You need to adjust the window so that you can see where the two equations intersect each other. So that's a big part of the question, is understanding how to adjust the window. We're starting at a population of we're starting at time equals 0. X represents the time. So we're going from 0, 1900 all the way to 2000 represents 100 years. Let's go to 200 years and scale by 20. And we're looking at, let's go ahead and start with the 0 population and go all the way to, I don't know, 1,500,000. And scale by 150,000. And let's see. Hopefully we see a decent looking graph. There's one population. And there is our other population. Alright, excellent. So we have a window where we can identify where they're both equal to each other right here. We need to go to second trace, intersect, and that allows us to find the point of intersection between the two. So go to the point of intersection, hit enter 3 times, and it looks like 135.5, so I'm going to round to 136. So I'm going to add 136 onto 1900 to come up with the time when the populations will be equal to each other. So we see that our two populations are going to be equal to each other in 2036. We can't all be on our A game. I was easily distracted this time around, but thankfully some of us can always be on our A game. So let's end. Love it! Alright guys, I will see you in class. Study hard. And see you next time. I feel like I should end a little bit better than that. Gosh. You're awesome! Say something, Abby.
Ooga booga.
Alright.